actually, I prefer this technique to L'Hopital's rule because Taylor expansion allows us to resolve every indetermination in a way that L'Hopital's rule doesn't. Okay, and it's also many ways, many limits. L'Hopital's rule doesn't work, but Taylor will always work, right? So suppose we want to compute this limit, right? Well, how do we approach this working with Taylor's polynomials? Well, what we can do is we know that we have x squared in the denominator, right? So we want to expand these functions in the numerator up to x squared, and then we don't care about terms of small o of x squared, right? Because if we have small o of x squared divided by x squared, the limit of this is going to be 0. Okay, that's the definition of a small o of x squared, right? So let's see how we can expand that, right? Let's see the table. The cosine is 1 minus x squared divided by 2 plus small o of x squared. Now e to the x is 1 plus x squared divided by 2 plus small o of x squared, right? So now with that information, we can go here and say this is the limit when x goes to 0 of 1 minus x squared divided by 2. We can write the small o of x squared later, minus 1 minus x plus x squared over 2, and then we have plus x, and all of this plus small o of x squared. All of this divided by x squared, right? And now so here we have 1 cancel out, x cancel out, and we have x squared and sorry, this is minus x squared, yes. Minus x squared divided by 2, right? So we have the limit when x goes to 0 of minus x squared plus small o of x squared divided by x squared. So this is going to be two different limits, right? The first limit is going to be minus 1, and the second limit is the limit when x goes to 0 of the small o of x squared divided by x squared. But we just said that this is going to be 0 because that's the definition of small o of x squared. So this limit is minus 1. Okay. You see how easy it was. Okay. If you know these approximations, you can just substitute and sum, and that's it, right? In this case, you could have applied L'Hopital's rule, but you would have needed to differentiate twice, right? In this case, you just need to do one approximation, and that's it, right? Okay, let's do another example. So we have the limit when x goes to 0 of e to the x minus the cosine of x divided by the sine of x squared. Okay, so here, yeah, we have done this before using L'Hopital's rule. You have to differentiate twice. Now here we can have again. What do we have in the denominator? Well, we know that the sine of y is y plus small o of y, right? And if we call y x squared, we know that the sine of x squared is x squared plus small o of x squared, right? So we can actually approximate everything in the numerator by up to small o of x squared, right? So we have done this before. E to the x is 1 plus x squared divided by 2 minus x, and then the cosine is minus 1 plus x squared divided by 2 plus small o of x squared divided by squared plus small o of x squared. And this is equal to 1 and 1 cancel out, x and minus x cancel out, and we have again x squared plus small o of x squared divided by x squared plus small o of x squared, right? And so yeah, you can either divide everything by x squared, or you can really see that this limit is going to be 1, right? You can separate the two things. Yeah, how to say this, right? This is going to be 1, right? Okay, let's see another one that's actually complicated. So here we have the limit when x goes to infinity of x squared times 1 minus the second of 1 over x, right? And again, in many cases when we deal with limits when x goes to infinity and 1 over x, we can change the variable to y equals 1 over x. So this is the limit when y goes to 0 of 1 minus the second of y divided by y squared, right? And the second is just 1 over the cosine, right? So this is the limit when y goes to 0 of 1 minus 1 over the cosine of y times y squared, right? So can we approximate 1 over the cosine? Well, you know, the cosine of y is 1 minus y squared over 2 plus small o of y squared, right? And so now we can write, let's see, let me get this here. We have the limit when y goes to 0 and then 1 over y squared. We have 1 minus 1 divided by 1 minus y squared over 2 plus small o of y squared. And then we can take everything in the same fraction, right? So we have the limit when y goes to 0 of, and then this is 1 minus y squared over 2 plus small o of y squared minus 1, right? All of this divided by, and then we have y squared minus, and then y squared times y squared over 2 is y to the fourth, but this is small o of y squared, so this is automatically small o of y squared, right? And then we have here and here cancel out, and the limit here is going, we just need to worry about these two guys because everything else is very small in comparison with these two, right? So the limit of this is going to be minus 1 half. As easy as that. Okay. So yeah, that's it. That's what you need to worry about. Okay. If you don't really get this, we can do an intermediate step, which is to divide everything by y squared. So then you have minus 1 half plus, and then 1 divided by lambda, 1 divided by y squared times small o of y squared is small o of 1. So this is small o of 1. And then we have 1 plus small o of 1. And if you just take the limit of small o of 1 is 0, right? So that's 0, 0, and you have minus 1 half. Okay, this is this intermediate step if you want to do it. But the idea is that this is very small compared to this, so the limit you don't really want to consider them, right? Okay, so that's just how to apply Taylor's polynomials to computing limits.